Hello, my name is Mark Joseph Eleuterio Angcos, and I'm here to present my group's calculator schematic that I've designed. The requirements for the project is to have a two-digit BCD number and have the calculator add those two-digit numbers to each other and have a function of subtracting and adding both. So first is we're gonna for the first part we're gonna explore the error detection design that error detection that I've designed. Next is the process of the whole adder and how it just works, how it works overall. So let's first explain the error detection. So the error detection here is basically dip switches and an LED indicator on your BCD inputs. So if we put a BCD inputs here like 1, we can see that it's 1. Why? Because I've added a comparator here. This comparator basically compares the input to a preset or already established BCD number, which is 9. So I put here 9 as the BCD, let's see, a BCD, 9 as a BCD default to compare. So if our input here is 1, it's gonna compare with 9. So it's either greater than, less than, or B. In this case, our A, which is our input, is less than B, which is our 9. So it so it outputs a high in our AND gates here because high in it'll allow the input to go here. So same thing with 2. So if A is less than B, which is true all the time because I have inputted none, which is 0, which is the comparator is going to compare 0 to 9, so it's always going to be true. Basically 0 is less than B, less than 0 is indeed less than 9. So this OR gate here is always going to be high, and it is going to allow the inputs to pass through into to the 7447 or the decoder. There we go. So that's basically it for the error detection. And now I'm gonna present to you what would happen if you input an error. So as you can see here, I've inputted 9. As you see here, I inputted 9. It's been displayed here. So if when I inputted 9, it's still gonna be output a good. Why? Because I've connected the other end of the OR gate to an equal sign. So if A is equals to B, it's still gonna be high. But if we input a 10, as you can see, it's 0 in this red LED, which is before green LED, which is indicates you that your input is correct. But when the red LED turns on, that means that you have inputted a wrong input or an invalid input, which is 10 is in binary coded in 10 in BCD is invalid because BCD only allows 1 to 9, and that's it. So as you can see here, this is 1010, which is binary equivalent to the number 10. This turns, this makes the state of A is less than B, which is false because we're inputting a 10 and comparing it to 9. So that's a false. A is equals to B, that's also a false because 10 is greater than B. That's why this A 10 is greater, A is greater than B is lighting up and indicates you that you have an error input. So that turns the OR gate to a low state. So it'll change to a low state. So it'll turn off the input or passageway of the input. So as you can see here, this is basically input C because with A B C D. So this is input C is not gonna go pass through here because the OR gate or the comparator won't allow it because it's not less than 9 and it's not equal to 9. So that's basically it. This is the indicators right here. There are the indicators, and this is the OR gate. And we're gonna output 0, which means you have an error input. So I'm just gonna turn it back on. And that is basically the error detection for all the 4 inputs that we have made. Next is gonna explain the part here, which is the SPDT, which is a single pull double throw switch for our modes. So if switch is high, or it's gonna this the first prong of the switch is gonna be connected to a power and one's for the ground. If the switch is being connected to the power, it'll be go into subtraction mode, which is I've set here. and in addition mode it's gonna be going to ground. Now I'm gonna explain to you addition first, so it'll be easier to explain. It's so I think I'm gonna change my mind. I'm gonna explain subtraction mode first. So we're gonna turn. So the process that I've chosen is to have a nines complement subtraction. So nines complement subtraction is basically a formula or a step-by-step way on how to subtract BCD numbers to each other. So in nines comp subtraction, typically it's the same as binary extraction. For the first step is basically the same, which is you invert your inputs by using SOR gates. Now, since our our data line or our mode is high because of its subtraction, so it'll inverse all of the inputs, which is 00 to a 1111, as you can see here. So it's 111 here. Next is that's gonna be powered up and added to 10. Why? Because typically if you subtract something, you invert and you add 1. So this turn is basically invert, add 1, and add 9. So that's why it's 10 there. Because in 9's complement, you need to subtract the input to 9. And this will output 9, as you can see here. Because you add 10 to a 111, it'll input 9. The C out here or C4 is gonna be ignored. So if we go down here, it's basically carrying, because that we don't have an input in our second digit, because this is the first digit or the first in segment, and this is the wait a minute, pause.